A centrifugal fan does not push air forward the way a propeller does, it throws air outward. That single difference is why it can keep delivering against duct resistance that would stall an axial fan. We are going to build this machine one part at a time, then take a real one apart. Air arrives at the inlet traveling along the shaft axis. The inlet ring accelerates it smoothly and turns it 90 degrees into the blade passage. How clean that turn is matters, because whatever distortion you feed the blades here, the blades cannot fix later. Inside the passage, the blades do the only real work in the machine. They grip the air and force it to rotate with the wheel, so the air leaves the tip carrying far more angular momentum than it had at the hub. That change in momentum is the energy input, and everything else is bookkeeping. The rotating air is thrown outward by centrifugal effect, which raises its pressure directly on the way through the passage. It also leaves the tip moving fast, carrying a large share of the energy as velocity. So you hold two currencies, pressure you already have, and velocity you still have to convert. That is what the scroll housing is for. Its cross-section widens toward the outlet, so the air slows down and its velocity turns into static pressure before it ever reaches the duct. Remove the scroll and you have a plug fan, which discharges into a plenum instead and trades some of that recovery for a shorter and more flexible installation. Now let us take a real one apart. What you are watching is the exact production geometry of a 190mm backward curved fan, pulled straight from the controlled engineering model and separated along its own axis. 6 parts, and every one of them has a job. At the top, the inlet ring that shapes the entering air. Below it, the impeller itself, the only part that adds energy. Then the rotor hub it is clamped to, the stator housing that drives it, the mounting plate that carries the load into your equipment, and finally the terminal box where power and control arrive. Watch it close back up and you can see how little space is wasted. Here is that same kind of part in the flesh, with nothing built around it. A bare centrifugal impeller, mounted on a balancing machine with a sensor probe riding against it. Every wheel leaves forming and welding with a small mass asymmetry, and this is the step where that asymmetry gets measured and corrected before the wheel is ever assembled into a fan. And this is the finished article. From the inlet side you can see the curve of the blades, the inlet ring, and the cast rotation arrow. Turn it around and the wheel is sitting directly on the face of an electronically commutated motor, so the rotor and the impeller are one assembly, with no belt, no coupling, and no separate drive. Now the choice that changes everything: which way the blades lean. Forward curved blades lean into the direction of rotation and fling the air out fast. Radial blades stand straight. Backward curved blades lean away from rotation, so the air leaves the tip more slowly relative to the ground, even though the wheel is turning just as fast. Here is the part that catches people out. Because a backward curved wheel throws less velocity at a given tip speed, its shaft power flattens and then falls away as flow increases, instead of climbing. A forward curved wheel keeps demanding more power the more air it moves, which is why an oversized duct or a missing filter can pull its motor into overload. Blade shape decides that behavior, not the label on the motor. One thing the fan alone can never tell you is how much air you will actually get. The fan has a curve, your ductwork has a curve, and the only flow that exists is where the two cross. Change a filter, add a bend, close a damper, and the crossing point moves. That is why a fan which performed perfectly on one job can disappoint on the next, and why a selection is only as good as the duty point you hand over with it.